Our next presenter is Chris Hoybor. All right. Chris Hoybor is the lead hydrologist with the water well driller, pump installer, and weather modification programs in the compliance division. He has a BS in environmental geology from Northwest Missouri State University. Chris has worked for TDLR, Texas Department of Licensing and Regulation, since 2023. His duties include conducting on-site inspections and data collection for water wells across Texas, and working closely with water well drillers, landowners, and other agencies to assist with reported complaints. Please welcome Chris. Thank you.
Are we good? Good morning. My name is Chris, as he said. I work for the Texas Department of Licensing and Regulation. Today we're going to go over our rules, our laws, and a little bit about Texas aquifers and groundwater quality. We are the water well driller and pump installer program with TDLR. Here's our contact information. I would say there are situations where this information is needed. I know with TCEQ, you guys primarily deal with public water supply systems. We deal with essentially all other wells. So if there are any issues with other wells, you can grab this information to contact us directly. What we do, first and foremost, we do groundwater protection. We do that through a few ways, mainly by licensing the drillers and pump installers. So we house their license, and we also establish and enforce the minimum well construction, well plugging, and pump installation standards. So essentially, we set in place rules to ensure groundwater protection, and that the drillers and pump installers follow those rules. We also house the abandoned well notification and enforcement program. We'll get into that a little bit later on, into a little bit more detail. We essentially work with other agencies to ensure groundwater protection, mainly being TCEQ, Railroad Commission, USGS, groundwater districts, you name it. We work with everybody. I do want to point out our website. We have made some changes on this website, so I wanted to let you guys know, and we do have a bunch of useful information there. If you go to tdlr.gov, the way to get to our page is through the red circle, through regulated industries, and then you'll go down to water well drillers and pump installers, and this is what it'll look like. There's a bunch of links here, a bunch of useful information that I would suggest everybody look at if you're dealing with wells other than public supply wells, mainly being, I wanted to draw your attention to that circle, our laws and rules. Like I said, there's a bunch of information that's on there. Mainly, you can see well reports, plug-in reports, which is useful information. You can see our laws and rules, and most importantly, what I wanted to discuss with you guys is reporting abandoned wells. If you do, because a lot of people are in the field and have visibility of these wells, through our website is how you're going to let us know or report those wells. So what we do, we ensure groundwater protection by setting standards for well construction. Here are a couple examples of what that should not look like. This is some examples of surface completion. So we set some standards for surface completion to ensure surface contamination doesn't occur into that individual well. And here you can see that that's not the case. If this area were to flood, if there were any contamination in that water, this has the potential to get directly into that aquifer or into that well directly. So we have a few different ways that we allow surface completion. This example is going to be a surface slab, and we have individual requirements for each one of these surface completion types. So I'll just go over that. This is going to be a surface slab. The requirement for a slab is going to be 2 feet on the outside of, or on each side of the casing. That has to be 4 inches thick. The casing has to be 12 inches above ground surface. And underneath that slab, we require a minimum of 10 feet of annular cement to essentially block that annular space and surface contamination from entering the well. There is also the option to do 2 feet of annular cement on top of 8 feet of bentonite grout if the water composition or the area, the type of well that you're drilling allows bentonite. In all of our wells, we do require 3 inches greater in diameter than the outer diameter of the casing. This is to ensure that there's enough space to allow that cement to set. And we also require or recommend 10 feet of annular grout above the filter pack as well, just some additional seal to stop contamination. Here is an example in the field of what our type of wells look like. It's, like I said before, it's not quite what the public supply wells are, but they do look pretty similar. This is a good surface slab, and in the bottom right you can see there's a little hole. We do also do field inspections of these wells to ensure that the driller has met the required specifications of that. The next type of surface completion is going to be a surface sleeve. The requirements for a surface sleeve are going to be the sleeve has to be 2 inches greater in diameter than the outer diameter of the casing. It must be made of 3/16-inch steel or Schedule 80 PVC. That also has to be sun resistant. The sleeve itself has to be 24 inches in length, 12 inches above ground surface and 12 inches below. And again, we require 10 feet of annular cement underneath that surface completion, or 2 feet of annular cement on top of 8 feet of bentonite grout. Again, we do require 3 inches greater in diameter, the borehole to be 3 inches greater in diameter than the outer diameter of the casing. And it is also recommended that they do 10 feet of annular grout above the filter pack. Here are some examples of what that looks like in the field. And as you can imagine, these are a little bit easier to do the inspections on. You don't have to tunnel quite as far, but there's a lot of miscommunication about the type of sleeve that's required. On the right, you can see that that is the sun-resistant PVC, Schedule 80, that is required. In some areas of the state that are more prone to freezing, we allow pitless adapters, which essentially is the equipment, the pressure tank that you would see above surface. We allow in a tank next to the well itself. In this type of completion or this type of well, we would require 20 feet of annular cement underneath that 90. With all three types of these surface completions, we also set spacing requirements, setbacks for the well. So our wells have to be 50 feet away from the property line, 150 feet away from any concentrated source of potential contamination, 100 feet from any septic system absorption field or spray area, or 50 feet away from any watertight sewage and liquid waste collection facility. We also offer another type of completion that allows for a better seal, essentially. This would be 100 feet of annular cement or to the top of the production zone, or 2 feet of annular cement on top of 98 feet of bentonite grout. Like I said, this is really just a better seal, and there are a few requirements on the grouting method, which is we would allow the Halliburton method, the Trimmy line, or the grout pump. With this type of completion or this type of seal, it does change our setback requirements. It brings our setbacks to 5 feet away from the property line, 50 feet away from any concentrated source of potential contamination, septic system absorption field or spray area, or watertight sewage and liquid waste collection facility. Essentially, we also have a process of a variance, right? So if a driller can't meet the requirements, they can submit a variance to us, and we would allow, or we would look at that and see if what they're proposing to do would cause contamination. And most of the time, this is what we would require them to do, is this alternate type of seal, which once again is just a better seal for protection against contamination. There are a few exemptions to the property line distance requirements. Exemptions isn't a great word for that. Essentially, the state sets the minimum requirements, but there are other organizations or agencies that can put other regulations on top of ours, so they can't go below ours. They can set additional requirements. Mainly groundwater districts have the ability to do that across the state. We do have specifications for wells that are completed in flood-prone areas, and this is essentially a steel sleeve extending a minimum of 36 inches above ground surface or 24 inches below. This is to allow protection if that area was to flood and any debris would be carried by that water. The top of the casing would be protected. Aside from surface completion, we also set requirements for downhole construction. We have rules set in place that unless waived by the landowner, a licensee shall use manufactured well screen and select the correct slot size for the screen to prevent sand or sediment from entering the well. We also have this for pump installers that they have to use manufacturer's recommended sizing and wire specifications. This is a picture of what that waiver looks like. I think we have an updated version, but this was the old waiver. And what we mean by this construction or manufacturer's construction materials is on the left, you can see a picture of some vertical saw cuts, right? So people have blank casing that they would essentially cut holes into to allow water in. And while this does allow water, it greatly reduces the structural integrity of that casing, which you can see on the right. If that does happen, the casing itself was buckled in. And this is a couple camera runs that we did. But it's a pretty good example of what can happen if non-manufactured materials are used. So we just try and avoid that. We also have specifications for the casing materials. Plastic casing, steel casing, fiberglass casing can all be used. And for monitoring wells, we have some other technologies such as Teflon, fiberglass, reinforced epoxy, a couple things that can be used. Commingling. We have a pretty unique perspective dealing with individual aquifers across the state. In certain areas, there are multiple aquifers in the same well that's drilled, or you're drilling through multiple aquifers. So we have some rules in place that essentially say all wells shall be completed so that aquifers or zones containing waters that differ in chemical quality are not allowed to commingle through the borehole casing annulus or filter pack to cause quality degradation of any aquifer or zone. This is a pretty vague term or wording of commingling. There are a lot of applications that cause this to not really apply. But this is a good example of our dealing with the individual aquifers and their water qualities. If a driller or pump installer encounters injurious water, so essentially those bad zones that we're talking about, they have 24 hours to notify the landowner and 30 days to notify us that they did encounter that injurious water. So water that could be dangerous to other groundwater. We also have the requirement that if they do encounter that, they have to, as quickly as possible, plug, repair, or properly complete the well so to avoid injury or pollution. And I know this is a lot of what TCEQ deals with is the plugging side of it, but we'll get to that here in a minute. Here are some specifications that if there is injurious water that is encountered, what our requirements are. And a better version of this is going to be just viewing the visual here. So essentially, if you have injurious water, so an aquifer that has bad water above the water that you're producing, we do have a requirement for you to pressure grout the injurious water off, along with all of our other protections, the surface completion, the annular seal, that all still stands. If you have fresh water overlying the injurious water, so your production zone is above the injurious water, essentially you've plugged too far, or you've drilled too far, plug back to the production zone. And there are situations where there are individuals who are producing injurious water. So if you don't care about the quality, you just want gallons per minute, you can produce injurious water. And in those situations, we require the freshwater zone to be sealed off, essentially not to allow this to commingle. This is just the rule that says that the licensed driller shall ensure that when injurious water or constituents are knowingly encountered, the well be plugged or converted into a monitoring well. There's also a piece on the bottom there that involves TCEQ. A driller must comply with all applicable requirements of the TCEQ 30 TAC, Chapter 331, while drilling a Class 5 injection well. We do run into situations where so we have the responsibility of the driller to inform the landowner. And there are situations where the landowner doesn't want that to occur. They want the water regardless of what it's going to cost or don't want to pay that cost. So within 48 hours of that landowner refusing the driller to do what they need to do in that situation, we require the driller to let us know that that's the case, just so we are aware of that injurious water as well. Essentially, in all of these situations, the well producing injurious water or the well encountering injurious water would be considered a deteriorated well because it has the ability to lessen or contaminate groundwater, either surface water or groundwater across the state. So a part of our abandoned well program is that all deteriorated wells must be plugged and all abandoned wells must be capped or plugged. We have a process for this. It's essentially, it gets reported, we inspect the well, make a determination on what needs to happen, and we allow 180 days after we've notified what the outcome needs to be for that to occur. With that, let's get into abandoned and deteriorated wells. Abandoned and deteriorated wells are a very big issue for groundwater in the state of Texas. It's estimated that there's 100,000. If you're in the field, I know I speak with drillers all the time, there are a lot more than that. And they pose a very big risk to the groundwater that we are producing. So essentially, they need to be taken care of. And this is where I would stop and ask everybody, if you are in the field or if you know of these wells, we rely on reports from individuals to do something about those wells. So if you do see them, make sure to go to the website and get it reported so we can do something about it. TCEQ has a spot in their rules about abandoned wells, and that is essentially that they have to be tested every 5 years or as required by the executive director to prove that they are a non-deteriorated well. And if they are deteriorated, they must be plugged in accordance to our chapter. There are some questions about what does that mean? What does testing mean? Essentially, you have to prove that that well does not pose a threat to groundwater or surface water. That well has to not be an issue. And what the conclusion we came to is essentially the best way to do that is a camera run. There are some authorities that, like we have the ability to do camera runs if there's a report. There are groundwater districts that have cameras that can do camera runs. Essentially, we just have to make sure that the integrity of the inside of that well, as well as the surface completion, is all intact. So how do we define an abandoned well? An abandoned well is simply one that is not in use, and a deteriorated well is a well that, because of its current condition, will cause or is likely to cause pollution to any water of this state, including groundwater. So that is a pretty vague definition, but we really ease on the side of caution when we're dealing with groundwater. So if it has the potential, if there's corrosion in the casing, if there's holes in the casing, if the surface completion isn't done properly, we would consider that a deteriorated well, and something needs to be done about it. Here is a little bit of a better representation of what we're talking about. So on the left, we have a working well. Surface completion is intact. It meets all of our requirements. The annular seal is good. The casing integrity is good. The pump's intact, right? This is a working well. An abandoned well, everything could be working on the well, except the pump is cut, it's at the bottom. This would be an abandoned well. You do have the ability to fish that pump out, and then that well could be considered to be used in the future, which we would allow that well to be capped. The deteriorated well, the one on the right, is something that, because of the current condition of the well, right, there's holes in the casing, there's holes in the annular seal, that well could pose a threat to groundwater. That one would need to be plugged. And thanks to our friends over at the Edwards Aquifer Authority, we have a pretty good visual representation, I don't know if it's big on y'all's screen, of the impact of a abandoned well next to a new domestic well. The way that I like to talk to drillers about this is that no matter how well you complete the new well you're drilling, if that abandoned or deteriorated well is introducing contaminants, you're going to be pulling those contaminants on your new well, right? This is why something needs to be done about these abandoned wells, because of the threat that they pose. Here are just a couple examples of what they look like. They come in all shapes and sizes. I mean, a lot of these are, 60, 70, 80 years old, some even older, right? So they range in how we would identify them. But here's a pretty good example. On the left, you see a large diameter well, a well in a vault. There's no surface completion. And then on the right, it could be something as simple as just PVC sticking out of the ground. Regardless of what it looks like, if you have the inclination that it could be a well, we ask you to report it. On top of abandoned wells posing a threat to groundwater and surface water, they're also a risk to public safety. Here's a couple examples of 4-year-old rescued after falling down a 44-foot well. There's a lot of bad stories like this, and there's much more than just this, right? They're not only a risk to groundwater, they're also a risk to public safety. On top of public safety, they're also an issue for wildlife. In this example, livestock. I know this example here was somebody's prize calf that had fallen into a well and was no longer considered their prize calf. So it's something that, even if they don't pose a threat to groundwater, it's something that we still need to get taken care of. Here's our rule that states essentially that the licensee that we have has a responsibility to notify the landowner that they have an abandoned well. And there's a big disconnect with our drillers and our landowners that this means that the driller is responsible for that well. That is not the case. In the case of abandoned or deteriorated wells, it is actually on the landowner. I urge them to get it reported because, it's at no cost, no additional cost for them. And here's where it states that in order to plug a well, you have to have a license. Either a pump installer, licensed driller, or the landowner themselves can plug a well. We do have a few specifications on plugging itself. So first and foremost, what we would require is that all surface completion is removed from the well. This is to ensure the best seal or plug when plugging the well. Next is that all removable casing is removed. And this is another kind of pain point with the drillers. The idea behind this is to ensure the best seal, that the plug gets on the backside, so on the outside of the casing. There are a lot of instances where you can't pull that casing out for whatever reason. It's caved in. I mean, there's a bunch. But in those cases, it goes back to the variance process that we have, and we would approve, that casing not being fully removed and that well still being plugged. There are also instances where, if we don't think it's going to get on the backside, if the plug is not going to, the structural integrity of that plug is not going to be great, we would require them to go down and essentially cut or shoot out the casing to ensure that there is cement on the backside. And then finally, the last requirement is that it has to be pressure cemented from the bottom to the top. And in this example, it's a trimmy pipe, but there are some others that can be done. In a lot of these old abandoned wells, specifically the large diameter wells that you see, there are a lot of them that are dry holes. And for dry holes, they don't have to be plugged. We actually would allow them to be backfilled with cuttings, native material, to the surface. So we also have wells that are considered grandfathered wells. And so it's wells drilled prior to June 1st, 1983 will be grandfathered without further modification. The issue is a lot of these wells do pose a threat to groundwater quality, right? So in that instance, we have the ability, even though they're grandfathered, to determine that they're an issue to groundwater and treat them as abandoned wells. So they would need to be plugged, recompleted, whatever that may be. So we have a pretty unique perspective of dealing with aquifers. We deal with complaints about all types of wells, and all of these wells are drilled across the state. So we cover the entire state. We have to know a little bit of information about all of those wells. So essentially, what aquifer are they pulling from? What are the contaminants in that aquifer? We have a very basic knowledge of that, but we have to know a little bit about all of them. So what is an aquifer? Aquifer is a geologic formation or group of formations or a part of a formation that contains sufficient saturated permeable material to yield significant quantities of water to wells or springs. We all know what an aquifer is. There are a couple different classifications that we deal with, specifically saturated versus unsaturated, tributary versus non-tributary, and most importantly, confined versus unconfined. So specifically confined, these are what we would consider artesian aquifers. They occur in what we would call the subcrop areas. So the outcrop is where it's going to be visible at the surface. The subcrop would be below. An unconfined aquifer is also known as water table aquifers. They typically occur in the outcrop area, and the water table is near atmospheric pressure, so that water is not pressurized. In confined aquifers, it is, and that's where you would see these artesian aquifers are free-flowing at the surface. It matters to us because if our drillers are drilling into a pressurized zone, a confined aquifer, that changes the way that they drill and the way that they complete that well. Here is a visual representation of that. As you can see, the blue is the aquifer itself, and the gray areas are those confining units, both above and below. This is what causes that pressure, once again, to allow the aquifer, the water in the aquifer, to be pressurized. Once again, just a very basic overview of what aquifers are and how we deal with them. We also deal with water quality. And I know, being TCEQ, you guys have much more specifics on water quality, but at TDLR, we only deal with very, very basic water quality types. Essentially, the way that we look at it is drillers can't change the quality of water. I mean, you can add filtration to individual homes for domestic wells, but the driller at the end of the day can't change what that water is, so we can't hold the driller accountable to that water quality. Hardness is one of the main ones that we deal with. I'm sure you know what it is, but it's the measure or concentration of calcium, magnesium, or strontium in the water. Issues that we see it poses is scale, that buildup on boilers, water heaters, pipes, big issues for individual homeowners that aren't on city water, right? They have to filter that out themselves. The other main factor we deal with is, when dealing with water quality, is total dissolved solids. It's essentially the approximate total amount of mineral constituents in the water. And I would like to point out the TDS, the TWDB, TDS classifications. Less than 1,000 milligrams per liter is considered fresh, 1,001 to 3,000, slightly saline, 3,001 to 10,000, moderately saline, 10,001 to 35,000, very saline, and above that is brine. Common constituents that we see. You guys have a much more in-depth guide to what these are and how to fix them. We just encounter them mostly naturally occurring in the aquifers themselves. So first, arsenic occurs naturally from sulfide ore deposits, but also in pesticides, waste disposal, agricultural drainage. So we see arsenic quite a bit. We were just dealing with something a little bit ago where arsenic was the potential issue, and it might be from some sort of refinery, but it could also be naturally occurring. So that's really on us to make that determination. Chloride, also relatively abundant, naturally occurring, but it is also present in sewage, oil-filled brines, industrial effluent, and seawater. Fluoride, I'm sure everybody here is familiar with what fluoride is, added to drinking water, but it is also naturally occurring through carbonate, volcanic, and sedimentary rocks. Iron, second most abundant metallic element in crustal rocks, so very much naturally occurring, and it is typically what we would see when dealing with water quality, is some sort of discoloration with iron, but it also comes from non-natural sources such as the casing, pipes, pumps, storage tanks. Anything that has metal and deals with water over time can cause that corrosion, and then we'd see that iron in the water. Manganese, also an abundant metallic element from igneous rocks, also in small amounts in sedimentary rocks, specifically dolomites and limestones. Sulfate, also naturally occurring. We'd see this from formations that have gypsum, iron, sulfides, but it's also from industrial uses such as mining and wastes. Radionuclides, also naturally occurring. We would typically see it present in the form of uranium. Okay, Texas aquifers. TWDB has defined 9 major aquifers and 22 minor aquifers. They define major as an aquifer that produces large amounts of water over large areas, and a minor aquifer as an aquifer that produces minor amounts of water over large areas or large amounts of water over small areas. Here is the map of the major aquifers that we have in Texas. This is a pretty good example of what we deal with, right? We cover the entire state when we're dealing with our water well drillers. So we have interaction with all of these aquifers. We have to know what their issues are, what we're dealing with, because when we get a complaint and the issue is iron, we have to know, is that naturally occurring in this aquifer? So we'll get into the individual aquifers. First, we have the Carrizo-Wilcox. It has confined and unconfined zones, consists of sand locally embedded with gravel, silt, clay, and lignite. Lignite is a huge issue that we've encountered with the Carrizo-Wilcox, specifically the production of hydrogen H2S and methane. We had a situation in Bastrop County where a well was producing methane, and the well was located on a high school parking lot. So we had to get fire department, the mayor was involved. It was a whole ordeal to get it taken care of and plugged properly, but that is just essentially what we would do in the case of an abandoned well. Here is the TDS map. This is from TWDB, and it's essentially what we would go off of, right? The areas of blue are the freshwater, areas of yellow, slightly saline, and above that is moderately saline. So the way that we would look at it is blue, good, yellow, serviceable, and darker yellow, you're getting into the risk of drinking that water. But in this area, you can see it's mostly good water. low TDS. It is hard water, but in the southern parts and the subcrop area, it can reach TDS of over about 1,000. And some of the issues we see with the Carrizo Wilcox, high iron and manganese, which is in excess of the secondary drinking water standards, and we also see in that southern region radionuclides. The Edwards Aquifer, one that we're over now, is a unconfined area or aquifer. Consists of partially dissolved limestone, which creates a highly permeable aquifer. As you can see, it's mostly fresh water, but it does in the southeastern zones get very, very high TDS. The aquifer itself is also what we would drill into it as hard water because of the aquifer composition. It is a limestone aquifer, so it is very, very hard water. It does have the issue of fluoride in the Barton Springs area, gross alpha radiation in the southern San Antonio segment. Another thing with the Edwards, it responds quickly to rainfall, drought, and pumping, which makes it very vulnerable to contamination, which is why we have those protected zones around Austin. The Edwards Trinity Plateau, it is a mostly unconfined aquifer. There are some small confined areas in the west. Consists of limestone, dolomite of the Edwards group, and sands of the Trinity group. The water ranges from fresh to slightly saline, TDS from about 400 to 1,000. Once again, it is considered hard water because of that aquifer composition, and it increases in salinity as you go west within that Trinity group. It does have radionuclides present in the northwest, nitrates, which exceed primary drinking water standards in the small amount of samples, and this study was done in 2016 by TWDB, and it also exceeds secondary drinking water standards for TDS. The Gulf Coast Aquifer has confined and unconfined zones. It is composed of discontinuous sand, silt, clay, and gravel beds, which is what we would typically see for an aquifer located there. It has generally, I would say, good water, less than 500 TDS in the northeastern zone, and the water quality declines as you move south into that lower yellow area that you see. The TDS reaches about up to 10,000 TDS. And areas along the coast are affected by increased salinity, possibly by saltwater intrusion from groundwater pumping, brine migration. There's a bunch of different speculations, but we do see that in the area. For the Gulf Coast Aquifer, we see arsenic and radionuclides that exceed primary drinking water standards in the southern region, so that area of yellow that we see. This is from the tufaceous sands of the Catahoula Formation. We also see iron, manganese in the north, chloride and TDS exceeding secondary drinking water standards in the south. The Huco Mesilla Bolson, it is a fully unconfined aquifer. It consists of deposits of silt, sand, gravel, clay, in separation of two basins, so the Huco and the Mesilla. In the Huco, it is slightly saline water ranging from 1,000 to 3,000, and in the Mesilla, it reaches TDS of almost 10,000 in some samples. In both basins, the water level declines, which have made the water more brackish. Arsenic is present, and there are some situations of chloride, fluoride, iron, manganese, sulfide. So essentially, there's a lot of contaminants in the Huco. The Ogallala, fun fact, it's the largest aquifer in the United States. It is a fully unconfined aquifer, consists of sand, gravel, clay, and silt. As you can see, TDS gets pretty bad, reaching about 1,000 as below the Canadian River. Arsenic, fluoride, nitrate, radionuclides, and selenium all exceed primary drinking water standards. And the nitrate could be attributed, not definitively, but to agricultural activity in the area. Pecos, it is an unconfined aquifer that consists of wind-blown deposits in the Pecos River Valley. TDS can reach up to 3,000, so typically good water, but it is also hard in the area. What we'd see in this one is high levels of chloride and sulfate, and lower levels of arsenic, fluoride, radionuclides in the south. The Seymour is an unconfined aquifer, consists mainly of discontinuous beds of poorly sorted gravel, conglomerate, sand, silty, and clay. In the south, it is very saline water. It can reach TDS of up to about 10,000, but in the north, it's generally good. Nitrate is present and it also exceeds chloride and sulfate throughout the aquifer. Last, let's do Trinity. Has confined and unconfined areas, consist of limestone, sand, clays, gravel, and conglomerates. Typically, good freshwater, TDS of less than 1,000, but in the south gets saline with TDS of up to about 5,000. And in the Seymour, we'd see, or in the Trinity, we'd see high sulfates and chloride concentrations. Here is a map of the minor aquifers. We won't get into those, but they are just as varied as the major aquifers, and in my opinion, more interesting, but we'll save that for a later date. All right. We have any questions?
Hi, I apologize if this is a basic question, but I was wondering, how are these aquifers, the demarcations made, especially when they're like next to each other?
So typically what we would see is it's not necessarily like an aerial outline, right? You'd also see that through a cross-section. So you'd see, this one aquifer stops in this area, but this other aquifer below that continues in that same area. So that's how we draw those outer barriers of those aquifers. We can track it not only aerially, but through that cross-section. All right, I think we're out of time. Like I said, we'll be downstairs with our booth if you have any questions, but I appreciate your time.
Thank you, Chris.
Yes. Thanks, Chris.